When connecting an electric vehicle to the power grid, you immediately face a physics problem. The grid and car don't speak the same electrical language. The global power grid pushes electricity in alternating current, or AC, but the lithium-ion battery pack sitting under the floorboards of the car strictly requires direct current, or DC, to store that energy. You cannot fix that mismatch with a simple software patch. Forcing AC power to straighten out into DC power requires heavy, dense physical hardware that generates a tremendous amount of heat. That hardware is called the onboard charger, or OBC. It acts as the vehicle's internal gatekeeper. Every electron drawn from a standard wall outlet has to be physically processed through this dense array of capacitors and inductors before it can enter the battery. Because automakers have to physically fit this entire circuit board securely inside the car's chassis, they have to put strict caps on its size and weight. And a smaller board simply cannot process massive amounts of current quickly. That physical bottleneck is exactly why plugging into your garage will always take hours. The vehicle's internal hardware simply can't translate the energy any faster without melting. This internal setup drives level 1 and 2 charging. The grid supplies AC power, and the car does the heavy translation itself, creating a slow trickle. Filling a battery takes 4 to 12 hours, which works well overnight. But a cross-country road trip demands a completely different engineering approach. To charge a car in minutes, you have to bypass the vehicle's internal bottleneck entirely. This is level 3 fast charging. Instead of forcing the car to translate the power, engineers pull the AC to DC converter out of the vehicle and house it in massive offboard cabinets. With the size and weight restrictions gone, these external stations can blast upwards of 350 kilowatts of pure, ready-to-use DC directly into the battery cells. Relocating the heavy physical hardware into a stationary cabinet is the only way the physics of a 30-minute highway pit stop actually works. Pumping hundreds of amps of raw current straight from a cabinet into a car creates massive thermal friction inside the physical cable. If you relied on standard copper wiring to absorb that heat, the charging cable would have to be so thick and heavy that a person couldn't comfortably lift it off the stand. To keep the cables thin and pliable, manufacturers build an active closed-loop liquid cooling system right into the cord. A dedicated pump circulates a water glycol mixture through tiny channels alongside the copper, continuously stripping away the heat. The thermal challenge extends to the actual plug. Historically, accepting AC power at home and DC power on the road required two completely different, bulky sets of connector pins on the vehicle. Engineers eventually consolidated this architecture with the North American Charging Standard, or NACS. They designed a single, compact set of shared pins that dynamically handles both alternating and direct current, depending on what you plug into. Solving those extreme thermal demands and simplifying the physical interface is what makes high-voltage fast charging safe and accessible for everyday drivers. The moment those connector pins seat into the vehicle, the car and the charging station initiate a secure, high-speed digital handshake. This continuous dialogue is a strict safety requirement. A standard home circuit breaker trips under light stress, but an electric vehicle operates on an ungrounded 400 to 800 volt system that requires real-time oversight. To protect the user, specialized components called insulation monitoring devices constantly scan the entire circuit, actively hunting for the slightest electrical leak or resistance drop before it becomes a hazard. Because these systems are so highly managed, the flow of power doesn't have to be a one-way street. The massive reserves of direct current sitting in your driveway can actually reverse course. Advanced onboard chargers are capable of bidirectional flow. They take DC power from the battery, invert it back into AC, and push it outward to keep a house running during a blackout, or feed power back to the local utility to stabilize peak demand. These layers of safety protocols and bidirectional controls turn the EV into a mobile, intelligent asset capable of supporting the very infrastructure that feeds it.